density functional perturbation theory is applied to when a perturbation is an incoming photon of moderate energy, like not X-ray and not radio waves. So what is the aim of this lecture? It is what do we want to say about infrared Raman spectroscopy. So first of all, as we see, there are both methods to measure the phonon spectrum. So there are probes that will give you as an output the phonon frequencies of a material. It could be a molecule, a gas, or crystal. And we'll see which phonon modes can be measured with these techniques, and what is important, we try to see which is the cross-section of the material for infrared and for Raman, so which is the relative intensity of modes when they are probed with these methods. I'm not going to treat more advanced techniques like second-order Raman, resonant Raman, because like they would take an entire workshop just for that. Also, I'm not sure if it's implementing quantum express anyway. I never used this. Never did this kind of calculation. So which modes can be measured by infrared and Raman spectroscopy? I didn't know where to put this slide, so I put it at the beginning. But something which you have to keep in mind is that, first of all, if a mode is can be measured by infrared or Raman, depends on the symmetry of the mode. And when you do a calculation of with phonon, at the end of the first Q point of the calculation of the phonons of gamma, you will get this kind of printout. After the phonons frequencies, they are printed once and they are printed again once more, and you will have like the modes, you will have the energy in centimeter minus 1, and then you will have these extra columns. So the first here is the symmetry of the mode, which is important because experimentalists like to use these names when they talk about one mode or the other. Although they are sometimes a bit tricky because, especially for bidimensional materials, experimentalists like to use the name of the peak in the bulk material to refer to the peak in the layer, but the symmetry of the layer is different, so the symmetry group is different, so the actual mode is different. And sometimes the big letter is the same, and only this changes. Sometimes everything changes, so you need to go to the bulk and then sort of compare the frequencies to see what they're actually talking about. But what interests us in this case is this last column, which can have a capital I or capital R, and this just means if the mode is infrared active or Raman active. I think it is possible that a mode has still zero Raman or infrared cross-section even with the letter here, but the opposite is not true. Like if there is no I or no R here, there is no chance the mode will be measured with a simple infrared or first-order Raman spectroscopy. So it only depends on symmetry, so I want to do a full disclosure here. There are plenty of commercial or even free software packages that can do this symmetry analysis and give you the activity of the mode and can have internal tables of effective cross-section that can give you very quickly some idea of the spectrum, like in a few seconds, and they also have tables of built-in structures and so on. So very easy to use, although they only work for materials that are more or less well-known. They don't work for more exotic cases, for atoms which have strange configuration, and also they are somehow limited in accuracy. In accuracy, in the intensity, but also in the accuracy of the position of the modes. They cannot reach the accuracy of ab initio methods. So first of all, infrared spectroscopy. This is quite easy. You have a light source. You shine it through a sample, and then you filter it with a monochromator, and you examine it with a detector. Or you can put the monochromator either here or both, and then experimentalists like to do it in more sophisticated ways. Like you could have a coherent beam of light. You could split it and make it pass through your sample and through a reference, so you can compare the difference of intensity for two samples. Like I think in the time it took me to explain this, they already taught 2 different ways to do it. But the idea is pretty much this. So you have a light source, and you pass it through a sample, and you measure what's come out or what is reflected. And as I'm going to, so what actually I'm going to see is how this material absorbs or reflects the infrared radiation, like mostly how it absorbs the infrared radiation. What is important, and I'm only going to talk a little while, is if your sample is molecules, like molecules in a gas, then everything is disordered, or it could be a liquid, or it could be a powder. Like often the sample is not a perfect crystal, but it's a kind of powder, and it doesn't have really a macroscopic order. So in this case, the polarization of the light does not really matter. But if you have a nice crystal, then you can try to polarize the light and measure the polarization. The outcoming light also polarized, so in the same direction, in another direction, and this can give you more information. So there are many variants that you can do on top of this, but this I think not all of these possibilities are implemented in the code, but they are all just variants on top of these normal methods. And what is important is what we will see now. No, what we see a bit later, which is like how the electronic structure of the crystal reacts to the electric field. So infrared spectroscopy is the easier way to do this. You have light coming in, and you have the phonon spectrum, and pop, you excite a phonon, and you absorb a photon. I'm going to exchange the 2 words a lot during this talk, so if you don't understand, maybe stop me. So let's see a bit about these two, this particle and this quasi-particle, photon and phonon. The photon is a quantum of light. It has an energy which is related to its frequency with the constant h bar. It has a certain wavelength, which is omega over c. It has a certain amount of momentum, which is h bar over lambda. And then you can mix them and combine, and depends on what you want. You get these three quantities which are important. The phonon is not a real particle, it's a vibration of the solid. It has an energy which is also h bar times its vibrational frequency, which depends on its wave vector k. Well, q should be. It has a certain momentum, which is h bar times q, but there is a degree of freedom here, like because our material is periodic, also the momentum has a certain periodicity, so you can add or remove any vector of the reciprocal lattice, and this is still a perfectly good choice for the phonon momentum. Like when you do the calculation with phonon, normally you keep this q inside the first unit cell of the reciprocal lattice. A more natural choice could be to put q inside the Boolean zone, which is the Wigner cell of the reciprocal lattice. But any choice is equally good, and if you actually see how the atoms move, if you put an extra g, they actually move in exactly the same way. So this g is completely arbitrary. And then you have a frequency lambda, which is 1 over, well, frequency, a wavelength lambda, which is 1 over q. So let's see how this works out in practice. So a phonon will have, okay, this same as before. So we have a phonon which is the energy of the order of 1,000 centimeter minus 1, could be 200, could be 2,000, depends on the material, but this order of magnitude is this one. Which means that it has a momentum of between 0 and 0.1 h bar nanometers minus 1. So this is actually just the inverse of this. No, sorry, this is not the inverse of this. This is the important thing. The phonon, a photon with an energy of 1,000 centimeters minus 1, has a momentum which is actually just the inverse of this. So it is 10 to the minus 5 inverse nanometers. Let's say this is a strange unit, but it works in this to explain this. So we see that the amount of momentum carried by a photon, which is the same energy as a phonon, is much, much smaller. So when we're going to Okay, and if you add an extra g here, you're only making things worse because you're increasing the momentum. You cannot reduce it, like you cannot make any smaller. So this is P is just the inverse of the size of the unit cell. Let's say it is a minimum. The minimum wavelength of the phonon is the inverse size of the unit cell, and so this momentum is related to that. And so what happens that in order to conserve the momentum, when I try to absorb a photon, the only possibility is that the phonon is at gamma, or in the immediate vicinity of gamma. So with infrared spectroscopy, and as we see later also with Raman spectroscopy, in the first approximation, like when you have direct absorption of one photon by one phonon, you can only get the phonons at the gamma point. But a plus side of this limitation is that the wavelength of this photon is going to be on the order of some micrometers. So in infrared, this energy is in the order is in the infrared, and the corresponding wavelength is of, let's say, the very minimum case could be 1 micrometers and up to several. And for what matters to us, we can consider this electric field, like the electric field corresponding to the light radiation that produces this photon, to be constant over many unit cell, or like constant at all. It's the so-called long wavelength limit for the electric field. Okay, so let's move on. So how do we treat now the response of our system, our crystal, to a finite electric field? So the first approach is, let's just add an external electric field. V of the potential E will be equal to the charge, a certain vector E that codifies for the distance, dot R. So this is a constant electric field, but it has some problems. So first of all, when we if we move at a long distance, it diverges, it becomes infinite. And in periodic boundary condition, there is no limit, so our crystal is actually infinite. How do we fit this? And this comes down to a more fundamental question, which is that the operator R is ill-defined in the periodic boundary conditions, because I could move it by I can move the origin, I can translate by any lattice vector, and it should be the same, but this R breaks this translational symmetry. And there is another problem which I'm not going to treat at all, which is that even a small electric field could cause Zener tunneling of valence electron to the conduction band. And the solution to this problem is that we're going to completely ignore it, and we will only treat electric fields which are very small, where we can consider that any tunneling can be ignored. So this response to electric field has been treated by Gonze and Gonze-Lee and Baroni, Giannozzi, De Gironcoli, and Accorso in these papers. And they take two very different approaches, and I'm going to see the approach of Baroni and co-authors now. So we say that the problem is that the position operator R is ill-defined in periodic boundary condition. So as you saw yesterday, however, when I want to compute the variation of a wave function with respect to something, I'm only interested in this kind of sum, where I only have off-diagonal elements here with the perturbation in the center. So it's a bit small, I hope you can see. So this gave to the original authors this idea. It says, what if I recast this matrix element of the position operator psi r psi in this form, where I write it psi commutator of the Hamiltonian with the position operator at the other side, divided by the difference of energy. So if you see the algebra, this is very easy. Like, just get psi h psi, which gives you one energy, and then you get psi r psi, which is what I want, and then the other term, this cancel out this denominator, is like It's not nothing magic. It's just a very simple algebraic expansion. And what is interesting is that this commutator of the Hamiltonian with the position operator can be expressed also as a derivative with respect to R, which is sort of a periodic boundary condition expression of the position operator. And okay, this is the simplest possible form, but if the Hamiltonian is non-local, then you will have extra terms that come out here, which I'm not going to talk about, but makes everything a bit more complicated when you have ultrasound zero potential or even non-constrained zero potential with they have some non-local projectors. So with that said, let's see a bit from the beginning how the response to a finite electric field works. So the electric field inside our material is defined as the external electric field E0 minus 4 pi the macroscopic polarization of the material. So it's important to see that if I apply a certain E0 on a sample, inside the material I actually have a field E. And when I'm doing my SCF calculation, I don't have the boundary, I don't have the external electric field really. So I will be working on this field and not this field. The polarization is induced by the E field or E0 field. It depends on how you see it, and it can be expressed in this form. So you have this normalization constant charge of the volume, and then you have the variation of the charge density with respect to the self-consistent electric field, like the actual internal electric field. And this variation with respect to electric field is a very similar expression to the one you saw yesterday for the variation of the charge density with respect to an harmonic polarization, which is just like the perturbable wave function times the ground state wave function summed over all the occupied states. So all these equations are in the paper. So it's not strictly necessary to write them down. Also, there are probably typing errors and stuff. So a problem with P is that it's ill-defined in periodic boundary condition because, well, this will take a bit of a digression because it depends on how you choose the origin of your crystal. And actually, only on the boundaries you have a net accumulation of charge on the two sides. Inside the charge moves, but it depends on if I watch it, if I look at it from one point or from the other point, it's not. You can get different values of P. Like if you don't look at it carefully. So we can do we recast it in a way that does not depend on the boundaries, which is this expression. So it is the macroscopic polarization along direction alpha, which can be x, y, z, or whatever system of orthogonal coordinates you prefer, and it is psi r, variation of psi, and here I use the formula from before, so first of all I had inside here a projector like a sum over all the occupied states, and then I use the formula from before to get rid of this r, and what I get is this equation. So you have a projection over psi, which I've used to bracket this r between two ground state wave functions. Inside I have the commutator, and then I have this, which is the variation of the charge density. So as you see, we are already getting close to where we want to go. Like this looks a bit like the equation of yesterday from the phonos. It's for an electric field, but it has the same ingredients. You have a sum of the states. You have the energy denominator. You have something that looks like a variation of charge density, and you have an operator which is now properly defined in periodic boundary condition, like it can be expressed and treated properly with the Fourier transform technique and plane waves and what we like to use. So we define this auxiliary wave function psi tilde, which is just this term here with an extra psi in front. And then we can set up it's called a set of self-consistent equations. So the first equation is this one. So you have the ground state Hamiltonian, like self-consistent Hamiltonian with the constant potential and all that, applied on the variation of the wave function, which is equal to minus C, minus the charge. And then you have the electric field acting on the this auxiliary quantity from before. And then you have a projection on the conduction band. And then you have the variation of the potential, like this is a variation of the external potential applied on the ground state wave function. So this is the usual projection on the conduction band, which, as you saw for the phonons, can be written as 1 minus projection on the valence wave function. So another bonus I get here is that I don't need to use empty states, which are infinite, and I can use only the I can do this with just the ground state occupied wave function, which are a small number and can be easily computed. And also, from a practical point of view, it's much easier to check convergence for this case. So this delta V is in the LF, because it's for long frequency, like it is the variation of the potential, and you have a term which is electrostatic response induced by the variation of charge density. So the charge density is modified, and it produces a certain electrostatic potential. And then you have the derivative of the functional with respect to this to the charge density multiplied by the variation of charge density. This is something you get also in this kind of equation. It is how the functional respond to variation of charge density, and then going to integrate this response with the actual amount of variation. So this is sort of a first order expansion of the exchange correlation potential, and it is quite difficult to treat in the most general case. And this is why when you go and see these more advanced linear response codes, they are always missing spin, they are missing Gaussian correction, they are missing every kind of more advanced functionals, because this term is very complicated to compute in general. But in the case of local density, it is just a numerical derivative, a derivative of the number n, which is charge density multiplied by the value of n. But like as you will see later, there are some of these formula is not implemented for spin, it's not implemented for GGA, and the reason is this term, which is really, it becomes quite huge when you have an exchange correlation potential which does not just depend on a number, but depends on the number, on the density, on its gradient, on the up density, down density, and then if you have other functional, can be also the second derivative, and so on and so forth. And okay, the variation of charge density, as you saw before, is the sum over all the occupied state of the variation of the wave function times the ground state wave function from the same band. And we solve this set of equations consistently. So we compute this starting with some initial trial. Then we compute this from these ingredients. Then we compute n from this equation. Like to go from this to this, it's trivial. Like it's just a matter of multiplying it by some operator, and then you iterate until you get to you get your stationary delta E, which solve the equation. Once you have all these ingredients, in the long wavelength limit, so when the electric field is constant in your sample, you can compute the electric tensor very, very easily. So you have the external potential, the external electric field E0, which is the internal field plus 4 pi polarization. And this can also be expressed as a sum of the electric field times the electric constant. So you do a derivative of this quantity E we have from before, from the equation here. And so you get this nice form for the electric constant, so the electric tensor or constant, depends if your material is anisotropic or not, which is a diagonal delta, and then this big constant, and just psi tilde times psi, and psi and the variation of psi summed over the occupied state. I want to say something like about the other approach, the one taken by Gonze. You can see the other papers. It is a completely different approach, and it gets to a different expression. So you observe that the electric tensor can be written also in this matrix can be written also in this way, and then you can compute this derivative. Oh, this is a very unlucky choice of letters, but it's the same as in the article of Gonze. So you have the total energy on top, and then you have the derivative with respect to two electric fields. They are all called E. You will see in this field, on this topic, everything is called either E, epsilon, or U. There is no other letters. And so you get an integral with a normalization in front, and then you get the variation of the wave function with respect to an electric field, and the derivative of the wave function with respect to its wave vector. So it is different expression, gives you the same value, the same quantity, like that you manipulate to get epsilon. And Phonon does not usually employ this formula, but it can if you ask it to, and you will see later how. And if you are familiar with the modern theory of polarization by Vanderbilt, Resta, Gonze, etc., you will notice that there is this factor, which is the derivative of the wave function with respect to each wave vectors which comes out. And it is not coincidental, actually, because Gonze takes a very phase approach when deriving this. So how do you ask Phonon to compute epsilon, the electric constant? You just set epsilon equal true value in input in the name list. If true, in a Q equals 0 calculation for a non-metal, the macroscopic electric constant of a system is computed. Do not set epsilon to true if you have a metallic system or the coding complaint, and stop. So note that this calculation takes quite a bit of time, because you have to compute the response with respect to the electric field. So in some case, you have a material which is an insulator. You may want to not compute the epsilon because you are not interested, or because you know that it has some value, or because you have already computed it once. And so it's nice, it's a good idea to set epsilon to false when you don't need it. However, there is a small quirk in how Phonon works. If you are doing a Phonon dispersion calculation, like if you're computing a regular grid, epsilon will always be set to true. And I found no way to set it to false. It will always compute epsilon. So if you are really on the limit of your computing time, you may want to do Q equals 0 by itself first, setting epsilon to false, and then do the rest of the grid. So it will not compute it. But OK, when you do a grid, actually, the time used for the electric field is not that big. But because it is a part of the code which is a bit less used than the rest, it has some, it can grow, like the amount of memory it requires can grow faster than other parts. So in some cases, it stops, it takes a long time here. So you take Q equals 0 apart, you do it without epsilon, and you can solve these problems. So of course, calculation of epsilon is not available for metal. We know that the metal have infinite the electric constant because they polarize, like they screen perfectly any electric field. However, the phonon code does not know if what you are computing is a real metal or it's going to be an insulated molecule, and you just put a small smearing to help convergence. And it will complain, it will stop anyway. So, well, if you can do the calculation without smearing, it's better. But if you know what you're doing, if you're sure that the smearing is not a real smearing, and you can just go inside the code, change the check, and let it compute epsilon anyway. And it will, of course, ignore the effect of partially filled, partially occupied bands. But when you're using a smearing and your system is not really a metal, it should be 0 anyway. So even if it is a fancy way to say that the bands are occupied up to a level, then they are empty, then what happens in practice is that they are just either full or empty, so it's the same as an insulator. I say this because some materials like graphene and so on, graphene I think is not particularly important, but where it is nice to see the electric constant, then you stub on this, you get stuck on this problem. And so either you do the calculation wrongly without the smearing, or you do it wrongly, or you cannot do epsilon. So sometimes you know what you're doing. You just go in the code, you remove the check, you do it. But don't do it if the system is a metal. In that case, we get random nonsense, and it doesn't work. So let's move a bit forward, because this is the electric constant. Okay, it's nice that it comes out of linear response, but of response to electric field, but it's not what we're interested in. We want to do infrared spectrum. So in order to arrive at infrared spectrum, let's talk a bit about phonons in ionic crystal. I think Andrea talked about this already a bit yesterday, so I go a bit fast. So this is like a zinc blend structure. We have positive and negative ions. And let's say you have a longitudinal phonon, so that moves the atoms in this way. So they move in a way that the planes of positive and negative charged atoms get closer or more distant to each other. If you freeze them in a certain position out of the equilibrium, the ions will produce a macroscopic polarization. I hope I put the arrow in the correct direction. I never remember. And we can define a quantity which are the effective charges Z star associated to a certain atom and to a certain direction of movement and direction of the charge, which is the derivative of the macroscopic polarization along direction beta when you move the certain atom I along direction alpha. This is just a definition. This, like I'm going to see this part in a way that's been done in the PhD thesis of Robert Tulip, which is available online. I give you all the links later. It is also done in the article of Gonzi, in the article of Baroni, but I think this way was a bit clearer for me. So one possible way to see this effect is to consider the electric enthalpy, which means the internal energy of the system plus its interaction with the rest of the world, external world, which in this case is just a macroscopic polarization. And so the energy is going to be the Kohn-Sham energy minus volume, and then the dot product of polarization with the induced electric field. This is some kind of thermodynamic with the electric field of the crystal. So you see that if I take the partial derivative of this enthalpy, I get the polarization. And so if I do the second derivative of this enthalpy, I get the effective charges. So effective charges are derivative of polarization. I plug this definition of polarization in the previous formula, and I get just that effective charges are minus derivative of this term. Here you can use, well, you can observe that this does not depend on the position of the atoms, and so I can express the effective charges as derivative of, I think there is partial here that has disappeared, derivative of the force with respect to an electric field computed at the equilibrium position of the atoms. Phonons, however, can do this in two different ways. So either you derive with respect to the electric field first, and so you get this expression, or you derive with respect to the displacement first, as we've seen before, you get this expression. So what's the difference? Okay, there is an implied sum over the occupied bands here. And you get the matrix element between the variation of the wave function with respect to the phonon and the ground state wave function, and as the perturbation inside, you get the perturbation induced by an electric field. Or here, you get the matrix element between the variation of the wave function induced by electric field, and as a perturbation, you put the derivative of the Hamiltonian with respect to atomic displacement, so either phonons or finite displacement in a real space. Something which is interesting to note, I don't know if, no. Something which is interesting to note is that in order to compute this, I do not need the variation of psi with respect to the phonon. And in order to compute this, I do not need, oh, sorry, contrary. In order to do this, I do not need the variation of psi with respect to the electric field. And in order to do this, I do not need a variation of psi with respect to the phonon. And so actually, if I'm using this form here, I do not need to compute also the phonon. And if I do use this form here, I do not need to compute the electric field. So this variation of the Hamiltonian is not so consistent. It's just a derivative. And so if you set everything like Z, all the parameters to true, they should give you the same result in the well-converged calculation. And so you have these two input parameters, ZEU and ZUE. Per default, ZEU comes in like it's computed when also epsilon is computed, because it needs the variation of the wave function with respect to electric field. And ZUE is computed by default if you do both phonons and epsilon, but I actually checked this, and you don't need to compute the electric constant. So computing the effective charge is cheap. On top of the phonon calculation, you only need to do a sum of the wave function, which is something you do many times during the cell consistency cycle. And as before, they can also be computed for metals, either real metals, fake metals. The code doesn't care. It doesn't let you compute them. They are normally zero in high symmetry materials, which is also something you need. Is interesting to test, like if they are exactly zero, if they are not exactly zero. It can be a good hint if your calculation is properly converged. I don't know if Andrea talked to you yesterday about this. So as we saw before, when you have the ions moving and generating a macroscopic polarization, this macroscopic polarization induces an electric field which acts as a pulling force, and so changes the frequency of your phonon. And one way to see how this effect works is to write the energy of the ions under a phonon, like a phonon perturbation, and inside an harmonic potential and an electric field. And this is the most general terms, where you have the harmonic oscillator, you have interaction between electric field and the electric constant, and you have this effective charge term, which gives you the interaction between these planes of positive and negative charge and the electric field. You can write the conjugate variables to U and E, which are respectively the force and the electrical induction, which are defined by the partial derivative of this with respect to the phonon and the electric field respectively, and you get these nice expressions. So go back to your book from the second year in the university. You get the Maxwell equations and put everything together, and you can solve this system, and you get that for the longitudinal phonon, the frequency, when you include also the effect of depolarization, is the frequency of the phonon, like without this long-term interaction, plus a term which depends on the effective charges and the mass of the atom and the electric constant, and you get that the transverse frequency doesn't change, like when you move the plane of charge like this, like if you don't change the distance, you don't have any polarization, so you don't get any correction. It's important to notice that this term is anisotropic, like this gives you the LO-TO splitting. It means that in the real vicinity of gamma, like what happens exactly at gamma is a bit more difficult to explain, but when you get very, very close to gamma, you will have that the energy of the mode depends on the direction. Not always, but in materials which are a bit less symmetric, it happens. And so if you don't keep in account this correction, it is very difficult to do the Fourier interpolation that you saw yesterday. So you must take this term out, do Fourier interpolation, put it back in. Otherwise, you will get what happens when you do Fourier transform of a square function. You get a lot of wiggles. It's also, I will say something about the experiment. You can, in experiment, often the sample has a bit of doping. Doping screens the long-range interaction, and so it will kill this contribution. How much it will kill it, it depends. A tiny doping can let the effect propagate for several unit cells. A higher doping will kill it very, very quickly. And so it is interesting when you compare it to experiment to try and see with and without effective charges. And so to understand how much the eventual screening caused by doping is going to influence the phonons. But okay, experimentalists are very aware of this problem, so they don't. They know that you're going to put the splitting, the LO-TO splitting, because of effective charges, and then you can. But okay, sometimes you don't see the longitudinal mode. You don't see it at the difference energy because it's screened by doping. So let me just draw something. So let's say one more word on this, because it is something which is a bit. It's a bit tricky, but when you understand it, it helps you in a lot of cases. So let's say you have your phonon, and here is gamma, and so you have the phonon like without the splitting that was like that, and you have a longitudinal split that send you your phonon here. And so let's say with a lot of doping, LO will go back here. So LO and TO are the same. There is no more splitting. With a little bit of doping, what happens is that you have the LO screening at shorten. You have the LO splitting at shorter wavelength, but then when you get to the very long wavelength, it's screened and it goes back to that, which is something which is almost impossible to see with phonons. If you are in this case, you have to a bit interpret it like using physical intuition, and you can expect this like this LO going back to the TO in some place between inside the Brillouin zone. You don't know exactly where. So how do you compute really the infrared cross section? Well, it's very easy. It is just a sum over the Cartesian direction. See, this is the cross section of a certain mode nu along direction alpha, and this is sum over beta, of course, not over alpha, of the effective charge with the polarization of the phonon mode. So in the case of molecules of disordered system, it like you don't need to care about polarization, but in the case of polarized light, you have to talk to the experimentalists to see exactly what they are doing, and it can be a bit more it can be a bit more complicated. So this is done by the dinmat.x code. Be careful, not matdin, but dinmat, which is a little code that reads the dynamical matrix for the gamma point and gives you the infrared cross section. So if it finds the effective charges and the electric constant, and the actual code that does this is this one. So it is really just a sum of over the atoms, the polarization of effective charges and phonon polarization multiplied by a constant and the factor 2 in front. And that's it. Constant is just the unit of measure. So I would say even if you can use dinmat.x, keep in mind that there's a limitation. It does not keep in account the polarization of the phonons. If you need anything else, it takes literally like one afternoon to write a small code in MATLAB or in Python, or even you can do it in Excel if you want, where you could put this yourself, starting from the phonon polarization that comes out of MATIN and the effective charges you can take from the output of phonon. So, but anyway, DINMAT writes it out in this form. So you have this is a molecule of CO2, carbon dioxide. So you see you have 5 modes which are 0, which are the 3 translational modes plus the rotations. And then you have the vibrational frequency of the molecule in centimeter-1 and in terahertz. And as you can see, you have the infrared cross-section of the relative intensity of the mode. As you can see, like these modes have very different intensity to each other. So it is not a completely trivial thing to compute this quantity, and it can give you a lot of information about your system to compare, like also the intensity and not just the position of the modes. It also depends on the mass of the atoms. We saw before there is a mass inside, and so you can try to see some effect of the isotope or stuff like that. Okay, so second part. Any question here, infrared? Before I move on. So, okay, you're all. So second part, Raman spectroscopy. What is Raman spectroscopy? It was invented by Sir Chandrasekhar Venkata Raman in 1928, or more or less, for which he won the Nobel Prize in 1930. It was immediately recognized as something valuable. He was working at the time with Krishnan, and Grigory Landberg and Leonid Mandelstam discovered the same effect, more or less in the same period, but they had no idea what they were seeing, so they didn't win the Nobel Prize. Raman is a very recognized physicist, especially in India. There are universities named to him. So what is Raman spectroscopy? You get a light source with a monochromator, which gives you a monochromatic light, which nowadays is almost always a laser light. You shine it on a sample, and then you detect what comes out. So you excite the sample with a monochromatic light, again more or less in the energy range that is absorbed by phonons, and you see that the spectrum of light coming out, like Sir Raman noticed that the spectrum of the light coming out was complex and had peaks and features, and so try to see what these peaks are. So what are they? So this is the infrared spectroscopy, what we saw before. You have light that excites one phonon, and you see this phonon. What is Raman spectroscopy? You shine a light of a higher energy, like let's say a visible light, usually green or something like that, and this one photon is absorbed, excite like the vibration of the crystal to a virtual energy state where there are many vibrations and the crystal is not relaxed yet, and then another photon is emitted with the same or a different wavelength. In the simpler case, the photon is absorbed and then it is immediately re-emitted, and so you don't see anything interesting. You put inside one light to get out the same light. This is called ray light elastic scattering. However, sometimes you put in one photon, you get out a photon of a different wavelength. It is because the system, instead of going down to the same state where it was before, it emits at the same time a photon and a phonon. And so there is a small difference in the energy. Or it could be that when the photon is absorbed, also a phonon is absorbed. And so you go to visual state, and then you go back to the initial state without re-emitting the same phonon as before. And so you see also a shift. This is why when talking about Raman spectroscopy, experimentalists always say Raman shift, because it is a change in the wavelength of the light you put in your crystal. And this ray light scattering is always often referred as the elastic peak of Raman, which you have at the zero of the Raman scale, Raman spectrum. So this is just what I just said. This is a very bad picture and quite grainy, but it was the only picture I could find on the internet where you can see the elastic peak here. So this is the Raman shift. How, like, I measure the light coming out respectively to the wavelength of the light I put in. And so at zero, which means the light goes in, comes out, same wavelength, you have a big peak here. And then you have a certain number of peaks. And it's important to notice that this elastic peak can be quite wide in some cases, especially if you have materials with heavy atoms. So like all the spectrum of the phonons is compressed toward the low energy because of the mass. And sometimes you get this elastic peak, which makes it a bit difficult to interpret the rest. Experimentalists fit it somehow and take it away, but you have to keep in account that this part of the spectrum can be less reliable than the rest. This is another case, another Raman shift I just found on the internet. You can see they covered up the elastic peak with this convenient green band. And then you have the Stokes spectrum and the anti-Stokes spectrum, which are in principle like in first order equivalent. And in our case, we will consider them as equivalent. But if you go and see higher order effects and more complex formalism, you see that there is a difference between the two. Like not only the relative intensity, but also in the not only in the global intensity of Stokes and anti-Stokes, but also in the relative intensity of the peaks. But this we will not see today. So how do you compute the Raman cross section? So the Raman intensity is proportional to this square modulus, where you have the Raman tensor, which we see what it is. You have the polarization of the light coming in, the polarization of the light going out. And then you have the Bose-Einstein occupation of the phonon mode and its energy. So this is something to notice, that this intensity is dependent on the temperature, but on the first order we can concentrate on this part here. I can ignore this part, and then it can be put back later, because it is actually diagonal in the phonon mode. So the tensor A is the response of our system of the electrons, actually of the charge density, with respect to two electric field and one phonon. So you have the electric field of the photon coming in, the electric field of the photon coming out, and a phonon that mediates these two photons. And then you have one of the square root of the mass and the phonon polarization. So the papers to reference for this kind of calculation is Porensag and Pedersen, 1996, and Michele Lazzi, Francesco Mauri from 2003. We see that Francesco Mauri comes out a lot when you do density functional perturbation theory, as it is very active in this field. So how do you compute the Raman tensor? The simple approach, and the one which is quite used a lot also nowadays, is to do finite derivation finite derivative of the dielectric matrix. You could see in phonon, you can compute the dielectric matrix without necessarily computing the phonons. So you could just use the first part of this phonon calculation, displacing the atoms, and do finite derivatives with respect to to the position of the atoms. And it has some advantages actually, because it's readily available. It does not require supercell. It works with PAW zero potential, with the ultrasound zero potential, with all the spin orbit coupling stuff, I think. And but it has some disadvantages, like that it scales quite bad with the system size, so it's very difficult to do this kind of calculation for many atoms. It is expensive for large systems, and it also has some kind of machinery that you need to do by hand, and it would be more convenient if it was already built in the code. So another approach is to see start from the definition of the density matrix rho, which is sum over the occupied state of the wave function, and to recast a derivative of the total energy expressed over the density matrix. So you have the derivative of the constant total energy with respect to a phonon in this case, which is 2 times the trace of the density matrix, which multiplies the partial derivative of the external potential with respect to a phonon. We noticed that the external potential does not change with an external electric field in the limit of long wavelengths, so we can recast this in this wave. So we have the third derivative of the constant energy with respect to one phonon, one electric field, one other electric field, is 2 times the trace. Second derivative of the density matrix with respect to electric field, and partial derivative of the external field. I again forgot the partial here with respect to the phonon. Something you notice immediately is that this derivative here only depends on alpha and beta, 2 Cartesian directions, so you can have one field along x, one along y. But actually, because I can exchange the order of the derivatives, I only have 6 independent terms, like xx, yy, zz, xy, xz, yz, while in the previous approach with finite differences, you had 3 times the number of atoms, finite displacement that you need to do. But you still need the second derivative of the density matrix. I'm not going into detail here also because it is very, very boring and difficult to do, let's say, on slides. I just tell that it has this expression. So you have the second derivative, the second variation of the wave function with respect to a perturbation. This is just generic perturbation lambda mu, but of course it's going to be electric field later. But so you have the second derivative of the wave function projected on the conduction band, and then you have the variation of the wave function on the ground state, and then you have the partial derivative, the variation of the wave function with respect to one and the other perturbation, and combined in several ways, plus the complex conjugates. So it is all a sort of ingredients, most of which we have already. Like this ingredient here we have already. This is computed when you do the electric constant. The ground state function, of course, we have them. What we miss is this second derivative here. So this is solved according to Lazari and Maury using a green function method. So you write this green function, which is the 2 conduction wave function and the energy denominator, and here you have the commutator of the constant potential derived with respect to one perturbation with the density matrix applied on a ground state wave function, and then you have the like this is the same as we did before for the the electric constant just seen in these different formalisms. And then when you derive once more, you get this expression where you again have this green function operator. You have the second derivative of the constant potential. And then you have commutators between the derivative of the density matrix and the derivative of the constant potential. So when you're going to see these things in the code, you need to implement, you don't understand anything, you have to keep in mind that every term has to be first order, has to be second order. So you have one derivative here, one here you have two derivatives, and this sort of, like pretty much you have all the possible combination of two derivatives combined together. So again, we have the problem of the operator R, which is ill-defined. It comes out in these derivatives here. And but again, we use this trick of writing the commutator of operator R with density matrix in this case, in this form, substitute it in the other equation, and we get this equation, which is a bit complicated, but in practical we have the matrix element of the commutator of the density matrix with respect, variation of the density matrix with respect to electric field, position operator, and two derivative of and two wave function. And this can be recast when you're doing periodic boundary condition in this other form, where there is something that comes out, which is the derivative of the wave function with respect to the wave vector. You will see we saw this in the formula of Gonze for the electric constant. So actually, when you're going to compute the Raman tensor, you get this term for free, and so you can compute the electric constant with the Gonze expression for free. So one critical component of calculation in practice is to check the convergence with the k-points grid. A bit because of this derivative here. Doing a derivative of a wave function with respect to the wave vector is a bit tricky because there is an arbitrary phase associated with each k-point which can appear. You can get rid of that with some method, but still you have to be a bit careful. But it is important to observe that all these expressions are not variational. So what you get is not a variational minimum of something, which means that you're not converged in a variational quantity. The first error will be second order with the amount of basis set you're missing, while these expressions are already have error in the first order. However, from practice, I noticed that this method usually converges faster than doing the finite differences with respect to the k-point grid. Then I don't think it's a theorem, so it's a bit depends on the system. But in the example, I could see you could actually you required less k-points to get the proper Raman tensor with this expression that doing finite differences. So the code will print out when you do a Raman calculation. The code will print out the electric constant computed with the first approach and with the Gonze approach, which requires different ingredients, and you have to check. You can check that they are the same to numerical accuracy. So again, if you are familiar with the Berry phase formalism, you will see that the things that go in the expression are more or less the same. This is not coincidence. They are more or less the same things that are important in this case. And actually, the derivation of Gonze uses Berry phase approach to derive these equations. And something which is also nice, but I didn't want to go in detail because it's quite cumbersome computationally, is that you can use the finite, the modern theory polarization, which is implemented in pw.x when you use the flag L if field equal true, to do finite differences with respect to an electric field. So you can actually apply an external electric field and do finite differences with respect to that. However, Phonon does not work with this. So it is not particularly effective way to study this problem, because we need to do derivative with respect to electric field and with respect to phonons, all by finite differences, so it becomes a huge mess of many calculations and differences and so on and so forth. But it's something you can do, and it can be nice to see once in your life when you're trying to start some job in this field, to see that you give the same result. So how do you compute the Raman tensor in practice? Or you set a Raman equal true in the input of phonon, and then you have three additional variables that you can use. One is the threshold for computing the variation of the wave functions, and then you have a threshold for the computing the non-consistent calculation, because when you're doing this derivative here, you need to compute the wave function at k and k plus a small q. And so this is the threshold for the calculation, and then you have a small delta which tells you how which controls the finite displacement of the k vector to compute the derivative of the wave functions. The code has some important limitations. So in particular, only non-constant zero potential, only local density approximation, so no GGA. I am sort of working on that, but it's not my priority. So if you really, really need the Raman tensor with PBE, you contact me, and maybe we can arrange to do it a bit faster. So all the rest of the code was done like 10 years ago. So this, I recently had to do this term for another case. So say, why not put in Raman? Why not? Because we don't have time. But it is more or less there. There is, if I remember correctly, very limited support for spin polarization. So I will just consider the average spin, and it doesn't work for metals. It's same story as before. You can enable if you want. Again, you don't need to compute the phonons in the same run as you compute the Raman tensor, because it only uses the derivative of the external potential with respect to harmonic perturbation and not the variation of the wave functions. So it may be a good idea to actually do Raman calculation without doing the phonon calculation, so that like if one of the two doesn't work, you don't waste twice the amount of computing time. But keep in mind that in this case, the code will not print out the dynamic mathematics file. So we need to do it by hand, let's say. We just write it on screen. Once we have the Raman tensor, it's quite easy to compute the cross-section. Again, this is done by the DINMAT code. And inside DINMAT, it uses a non-polarized formula, which works for molecule disordered systems. And again, the formula is really, really easy. You could just go to the file and open it and change it, import it in MATLAB and do it yourself. But also, it's something I plan to do one day, to put the formula with polarization of incoming and outgoing light. And here it is. Raman intensity is written on output. It's nice to observe that a mode which is not infrared active could be Raman active, and of course these modes which have zero frequency, you won't see anything because they are covered by the elastic peak. But yeah, this CO molecule is not particularly interesting, but still you can get the intensity. And you also get, in this particular case, this depolarization factor, which gives you how much depolarized light which is incoming will be non-polarized in the outcoming measurement. So Raman can only measure phonons at gamma, but in the second order Raman, you have two phonons which are emitted when one photon is absorbed, and they will be emitted with opposite momentum. This signal usually is very, very small, very difficult to measure, but there are some techniques to make it more, to be able to measure it. But this is a completely different story. I'm not going to talk about that. And you can use a resonant laser. So when you tune the incoming light to some phonon modes, some particular transition, and so you get a big enhancement of specific modes with respect to other. You get higher harmonics effects. Also, this is a completely different story. It is possible to simulate to some extent, but it's much more complicated. So to finish in the last 10 minutes, we talk something which is not electric field. And it's something I actually worked on instead of just studying it in the last weeks. And it's the phonon line width. So in reality, when you go and look at the phonon spectrum, this is something I grabbed just random on the internet, you will see that you don't have sharp peak as in the beautiful spectrum of NMR that Davide presented this morning, but you have this kind of potatoes of, in the best case, Lorentzian distributions around the frequency. This is because phonons are not, themselves don't have sharp energy as the NMR spectrum does. So each phonon has a bit spread in its energy, which can depend on several factors. So each peak is not a perfect energy delta. In the best case, it allows a narrow Lorentzian function around the frequency with a full width at maximum, which depends on the temperature. In the case of anharmonic materials, like materials which have interesting properties that we want to study usually, the main peak can have satellites, so you can have a Raman signal in areas where there is no Raman, where there is no phonon frequency, and all these features can appear and can disappear with the temperature, and are not explained by this model. So this is something I'm just going to talk you about, but we're not going to see this afternoon because it takes a completely different set of codes, and it's much more complicated to study, much longer calculations, and it would take 1 or 2 days just to go in details. So all this is pretty much work in progress. So if you expand the total energy around its minimum as a function of a harmonic phonon, you have a first order term, which is the force, which is 0, because we are at equilibrium. Then you have the second order term, which gives you the harmonic oscillator that gives the phonon. And then you get higher order term, a third order term. We have 3 atoms that move, and so on and so forth. So what we are going to do now is to treat the second order term as the basis set on which we're going to solve perturbatively the higher order perturbations. So what happens in practice is that phonons, which in the harmonic crystal have infinite lifetime, so they just oscillate forever, when you add the additional terms, you can have interaction between phonons. So you can have 2 phonons that merge into 1, or you can have 1 phonon that scatter into 2. And when this scatter happens, it could be either that the wave vector of the 3 phonons sum up to 0, or that they sum up to a G vector of the reciprocal lattice. So this is important in thermal transport, but not particularly in the case of phonon line width. So these interactions are not possible in a simple harmonic model. In a harmonic model, your phonons are your eigenstate of the ionic Hamiltonian. They don't interact. Once you excite a phonon, it stays there. With the first order in perturbation theory, you have this possible mechanism of interaction between phonons, which I'm going to see. So the tadpole diagram, this one here, is actually already included in the quasi-harmonic approximation level. So quasi-harmonic approximation you saw yesterday, it has, you can do it with respect to the volume of the unit cell, so you can see the phonon population at different volumes, fill it up with a certain temperature, find the minimum as a function of the volume and the temperature. And then you have this, the optical diagram, which is also quasi-harmonic, but when you have internal degrees of freedom, so when with respect to the position of the atoms. So you could move the atoms, compute the phonons, fill up the phonon population with a certain temperature, compute the enthalpy, and minimize this as a function of the position. So these are important, but like, let's say, we've already done it. Then you have the loop diagram, this one, which contributes only a shift to the phonon frequency, so it moves the phonon frequency a bit. And then you have the bubble diagram, this one, which contributes both a shift, it moves the phonon frequency a bit, and also has a line width. You see that, I don't know if you're familiar with Feynman diagrams, I'm not, but they tell me that these are third order vertices, so these come from the third derivative of the energy, and this is a fourth order vertex, so it comes from the fourth order derivative but all these diagrams are first-order perturbation theory. So it is incorrect, let's say, to treat only one and not the other, because they are all at the same order in perturbation theory, even if the vertex that go in are of different order. These are the mathematical the formulas for these terms. So tuple, we say we don't care. We can do it quasi-harmonic approximation. The loop, you have the fourth derivative of the energy, and you take it at the phonons with plus and minus q. So it is a bit of a special case, and multiply it by the Bose-Einstein occupation of the phonon energy, and it gives you a quantity which is real. It's a real number, and is a shift in the phonon frequency. The bubble is more complicated because I think this doesn't have battery anymore, but okay. Because you have the third order derivatives, modulus square, and then you have these terms where you have Bose-Einstein occupation and energy denominators. And these have a real part which gives you a shift of the phonon line, and an imaginary part which is minus the phonon scattering probability or lifetime. So as I said before, you need to consider all these diagrams together. You cannot put one and include the other. But as long as this is the only one which is an imaginary part, if I'm only interested in the imaginary part of the four of them, I can just take the imaginary part of this. And this is all that there is at first order perturbation theory. You see here we have this kind of denominators which are some Lorentzian functions. Like the imaginary part of these denominators are Lorentzian functions. I can take the imaginary part, convert them to Gaussian functions, and then express them as energy conservation deltas, which is convenient. And on the right, just the imaginary part of that diagram in this way, where you have the derivative of the potential of the ions, like on the total energy, which is a bit different from the one before. There are some constants which went inside the definition. And then you have these terms, which are like occupation of the initial and final phonon state. And these two terms are coalitions of two phonons going together, and scattering when one phonon splits in two, and is equal to the inverse lifetime or the scattering probability of specific phonon modes. So we need this V3. This can be done with perturbation theory. It is a third derivative of total energy, and so you have all these nice terms with external potential derived two times with the first response of the charge density, third derivative of the potential with the first response of the charge density. Then you have the functional derivative of the exchange correlation energy with the three response of the charge density. And then you have many additional terms because of metal, because of zero potential, because of Gaussian correction, because of spin, and so on and so forth. And it makes a lot of stuff to compute. But you can compute it. At least you can compute it with PBE and non-consigning zero potential. The code is called D3 code. It used to be part of the quantum espresso distribution, but it was a special case code which will only allow you to compute the line width at gamma. So I, with Michele Ladri and Francesco Mauri, been working a few years ago on a generalized version, which is still a bit fragile, doesn't work always perfectly. So we say it's still a bit experimental, but allows you to compute this quantity using perturbation theory and actually using the 2n+1 theorem, which comes again from Gonze, and allows you to compute the third derivative of the energy, knowing only the first variation of the wave function. It's not the only way to compute the third derivative of the energy, but it is a quite effective way. And so once you have this ingredient, you put them in, and you can compute the line width of the phonon. Here I put the phonon dispersion of graphene, and the colored band around is the line width of the phonon multiplied by a factor 100. Like graphene is very harmonic, so the phonons are actually a very narrow line. And so you can see that there are no big surprises for the most, but you have some funny places where you have strong transitions. So the phonon here is a big line width, so it means that there are two other phonons which have the correct energy and the correct momentum, and so this can decay a lot, and so on and so forth. But in a strongly, so this is okay for material like graphene, which is not very anharmonic. Material which are more anharmonic, instead of computing a line width associated with a certain phonon, you say, okay, it's the phonon itself which it's not a good quasi-particle for my system. And so what you can do is you can compute the spectral weight, I am not really sorry, directly, and which is this expression, which is more or less a real imaginary part of the diagrams and summed over the phonon modes, and which give you a spectrum of the phonon as a function of the energy, which is what you can measure actually by Raman or by NMR, or by neutron scattering. But keep in mind that this expression is wrong if you include only one diagram again. Now you have both real and imaginary part. So you need a way to treat the tadpole diagram, which we ignored before. And this can be done in several ways. It can be done with fourth derivative of the energy, but they start to be a bit too many terms. What we have done in some works is to treat it with some stochastic sampling of the position of the atoms. Other people do molecular dynamics and then extract it by fitting or by doing velocity correlation. And or you can just do finite differences if you want, or of the phonons or the forces or what else. But once you have like the shifted phonons and you get the imaginary part, you can put it in a formula, and you can get, like this is a spectrum of palladium hydride as a function of the energy. So you see you have these yellow peaks. This is not gamma. This is a point around halfway in the Brillouin zone, which are pretty much Lorentzian functions. Like they are very sharp and symmetric. But these modes which are associated with the hydrogen going a bit freely around between the palladium atoms have some interesting feature. It is not symmetric. It has satellite peaks. And if you compare it to just a superposition of line width, which is the red curve, you can see it is quite different. So it is possible in principle to combine the cross-section of Raman or infrared with this kind of calculation. As far as I know, nobody's done that. But it's just a matter of, like, here you still have a well distinct contribution from each mode, so you could mix the cross-section for the mode with the spectral function for the mode. It is not completely correct way to do things, but it's something. And actually, I think in this kind of more complicated system, you have many more uncertainty and approximation that go in, that just knowing if a mode will be active or not is quite interesting. So in the afternoon session, we will see how to compute infrared and Raman cross-section for a molecule of CO2 and for aluminum arsenide. And if there is time, I have prepared a small Python script that computes the Raman tensor by finite differences, and so we can compare the convergence of the two methods. This is not particularly interesting from a scientific point of view, but it has two nice didactic applications. Once you see how to do a Python script to run a quantum espresso. You can do it with AIDA, I think, as well, but I'm not expert in that. And two, you can see that actually what converges faster with the K points, with the cutoff, and how difficult it is to actually converge this beast to a very converged state. That's all. Thank you. On this shared folder, I put the lectures and all the papers cited. But I think they will be sent by email also in the school, probably. That's it.